Hi, I am Sukrut Rao from the Max Planck Institute for Informatics, and I will be presenting our work titled Towards Better Understanding Attribution Methods. The goal of this work is to perform a more systematic, fair, and holistic evaluation of attribution methods to better understand their strengths and shortcomings. While deep networks have been successful on tasks like image classification, it is a well-known problem that they are effectively black boxes, making their decisions difficult to explain. A class of approaches to mitigate this are attribution methods, which attempt to highlight input regions that were important to the model's decision. Based on their mechanism, they can broadly be classified as backpropagation-based, activation-based, and perturbation-based methods. However, since the model is a black box, there are no ground truth attributions, which makes it challenging to evaluate such methods. Common evaluation techniques include metrics that evaluate localization of attributions to object bounding boxes, or to grid cells from a grid of images, as is done in the recently proposed grid pointing game, or GridPG in short. This is then quantified, for instance, by measuring the fraction of positive attributions within the bounding box and the grid cell respectively. In our work, we propose schemes to better evaluate attribution methods along three different avenues. Our first contribution is an evaluation setting that disentangles the model from the attribution method. When measuring localization, such as in GridPG, one assumes that all positive evidence for the prediction lies within the bounding box. However, the model's decision might be influenced by information from other grid cells, for example, when there are semantically similar classes in the grid. So, to evaluate the model faithfulness of the attribution method, one needs to disentangle the behavior of the model from that of the method. To address this, we propose a complementary setting to GridPG called dfull. Starting from a grid input, we pass each grid cell separately through the CNN. A separate classification head is used per grid cell, which receives information only from its corresponding cell and has effectively zero connections to other grid cells. We then use this to generate attributions for each class in the grid. Unlike GridPG, this ensures that no other cell can influence the classifier's decision and demarcates where true attributions could possibly lie in an image. Full disconnection allows for a stronger evaluation setting where classes can repeat in the grid. Here, since the bottom right cell cannot influence the top left cell's output, any attribution given to the bottom right is necessarily erroneous and can help find failure cases in attribution methods. Our second contribution is a scheme to compare attribution methods more fairly. Different attribution methods are typically evaluated at different model depths. For example, some like input times gradient explain the full model, while others like GradCam explain only the classifier by weighing final layer activation maps, which is an easier task. For a fairer comparison, we evaluate at multiple identical depths, in particular at the input, at the final feature map, and at an intermediate layer. At each layer, attributions are obtained by treating activations at that layer as inputs and treating the remaining layers as the model to be explained. These attributions are then upsampled to the image dimensions. We find that diverse methods often perform similarly when compared on an equal footing. Our third contribution is a qualitative evaluation scheme for obtaining holistic visualizations of a method's performance. Attribution methods are typically evaluated qualitatively by looking at individual examples, but this is sensitive to the choice of examples as one can usually find examples both of attributions that perform well and poorly from any attribution method. We propose an aggregate attribution evaluation scheme, AGAT, which takes advantage of the grid cells aligning across the dataset. Choosing a specific grid cell, say the top left, we sort the attribution maps in descending order of localization score, bin them based on their positions in the sorted order, and finally aggregate them to obtain a succinct and holistic visual summary of a method's performance. We evaluate using grid inputs on GridPG and dfull at multiple layers, on ImageNet using VGG11 and ResNet 18. For each configuration, we qualitatively evaluate using AGAT visuals. On GridPG, we find that the localization performance of many methods improves towards the final layer. Further, we find that methods like input times gradient can perform similarly to top performing methods like GradCam when compared at the final layer. On dfull, we find that although visually noisy, backpropagation based methods generate attributions that localize perfectly. Further, we find that activation-based methods like GradCam fail to localize well and find via AGAT visuals that this is due to them attributing both instances of the repeated class at the top left and bottom right corners. Finally, we find that post-hoc smoothing of attributions using a Gaussian kernel can significantly improve localization for input times gradient and integrated gradients in some cases. Thank you for your attention.